We're now going to continue with looking for some of the parallels between what we studied in divisibility with integers and what we studied with divisibility in polynomials by looking at greatest common divisors and developing a Euclidean algorithm for polynomials. So first, we're going to define what the greatest common divisor of two polynomials is. We're going to develop a Euclidean algorithm for polynomials. And then we're going to look at an example. So I want to recall a theorem that we proved about greatest common divisors of integers. And that says if you have two integers a and b, then d is equal to the GCD of those two integers precisely when the following are true. When d is a common divisor of a and b, of course. Right? In other words, d divides a and d divides b. Whenever k is a common divisor of a and b, then k divides d. In other words, d is the biggest common divisor of a and b. That's a little bit deceptive because if you're worried about positive and negative integers, that can be a little bit problematic. But we clear that up by requiring that d is positive. Otherwise, both d and negative d will satisfy conditions 1 and 2, and that gives us two possibilities for greatest common divisors. So we need GCD to be a common divisor, we need it to be as big as possible, and perhaps something else to make it unique. So if f is a field, we want to ask the same question about polynomials. If we have a polynomial d of x and f of x, what does it mean for that to be the GCD of f of x and g of x? So it has to be a common divisor. That means d of x divides f of x and d of x divides g of x. If we have some other common divisor, some other polynomial k of x dividing f of x, k of x dividing g of x, then k of x divides d of x. That kind of tells us that d of x is the greatest of all the common divisors because everything else divides into it. And finally, to make it unique, instead of saying it's positive, which makes no sense when we talk about polynomials, we're going to say that the leading coefficient is 1. A fancy word for that is we demand that d of x is monic. So let's look at an example. Here's f of x and g of x, two polynomials. We can try factoring to find their GCD. Here's what the factoring looks like. F of x equals 2x minus 1 times x plus 1. G of x equals 2x minus 1 times 2x squared plus 3. Looks like the GCD is going to be 2x minus 1. However, that has a leading coefficient of 2, not 1, so it's not monic. But we can divide both sides by 2 to give us a GCD equal to x minus 1/2, just to make sure that that actually divides evenly into both of them. We can see that f of x equals x minus 1/2 times the quantity 2x plus 2. G of x equals x minus 1/2 times the quantity 4x squared plus 6. All right, so now what? Well, we generally have difficulties finding GCDs. First of all, just like with integers, factoring polynomials is hard. In fact, I would argue that it's even harder than factoring integers because we have those darn x's that we have to contend with. And when we factor something, that helps us guess what the GCD is, but the proof tends to be hard, right? So it's good for making accurate guesses, but in helping us prove things, it's pretty useless. So it might be helpful to have something like the Euclidean algorithm that we had for integers. We had those same issues with integers, more or less. Euclidean algorithm helped us eliminate those possibilities. So what did the Euclidean algorithm look like in the old days? Well, basically, it was this theorem that was used recursively to find the GCD. So if you have integers a and b, and if a is equal to bq plus r, then the GCD of a and b is equal to the GCD of b and r. And of course, this helps us convert finding GCD of big numbers into finding GCD of smaller numbers using the division algorithm, and we can keep on going. The theorem that is going to help us with the Euclidean algorithm for polynomials is going to look very similar. If f is a field and you have polynomials f of x and g of x and f of x, big F of x, if we have f of x equals q of x, g of x plus r of x, in other words, a division algorithm looking expression, then the GCD of f of x and g of x is equal to the GCD of g of x and r of x. And the proof of this is going to look almost identical to what it was for the Euclidean algorithm of integers. Just like before, we're going to prove the theorem by proving that all the common divisors of f of x and g of x are exactly the same as all the common divisors of g of x and r of x. If they have the same divisors, they'll certainly have the same greatest common divisor. So we're first going to assume that d of x divides f of x and d of x divides g of x. So it is a common divisor of f of x and g of x. And then we're going to show that d of x is a common divisor of g of x and r of x. So we'll write down our assumptions. F of x equals k of x times d of x is what it means for d of x to divide f of x. G of x equals m of x times d of x is what it means for d of x to divide g of x, where k of x and m of x are both polynomials. Our f of x is equal to q of x, g of x plus r of x. Right, that is by assumption. And if we plug in what we know about f of x and g of x in terms of d of x, we get k of x d of x equals q of x m of x d of x plus r of x. We put all the d of x stuff on one side. We're going to solve for r of x. That enables us to factor out of d of x. And then that equation allows us to say that d of x divides evenly into r of x. Since we already had d of x by g of x, that was part of our assumptions, then that means that d of x is a common divisor of g of x and r of x. Going the other way is going to be almost identical, except actually a little bit easier. We're going to assume that d of x divides g of x. We're going to assume that d of x divides r of x, so it's a common divisor of those. And then we're going to show that d of x divides both f of x and g of x. So once again, by assumption, we have g of x equals k of x d of x, and r of x equals m of x d of x, right? That's what it means for d of x to divide g of x and r of x. Now, when we write our assumption that f of x is equal to q of x times g of x plus r of x, now we can substitute those in for g of x and r of x on the right-hand side of the equation. That's what we get. Notice that we don't have to do any fancy algebra to factor out a d of x. So we get d of x times some polynomial. I don't care what it is, because d of x times any polynomial equals f of x is exactly what it means for d of x to divide f of x. And remember, our assumption at the beginning was, or one of our assumptions was that d of x divided g of x already. And so that means that d of x is a common divisor of f of x and g of x. And as I mentioned before, we now have proved that the common divisors of f of x and g of x are identical to those of g of x and r of x. In particular, that includes the greatest common divisor, which means that the greatest common divisor of f of x and g of x is equal to the greatest common divisor of g of x and r of x. Okay, so let's see how this works in practice. It shouldn't be too bad, right? Because we have the GCD of two polynomials. It looks very unpleasant, but if we take the smaller degree polynomial, divide it into the larger degree polynomial, that will help us narrow things down. So I'm not going to do the long division. I'll let you do it. It's a mess to show on my slides here. But when you do it, you'll note that your quotient is 2x minus 2. Your remainder is 10x minus 5. And therefore, writing that as an equation, you get 4x cubed minus 2x squared plus 6x minus 3 is equal to 2x minus 2 times 2x squared plus x minus 1 plus 10x minus 5. Now, the GCD that we're looking for is exactly the same as the GCD of the quotient and the remainder. So that means it's the same as the GCD of, or not the quotient and the remainder, the second polynomial and the remainder. So we get the GCD of 2x squared plus x minus 1 and 10x minus 5. We do long division again. We end up with a quotient of 1/5 x plus 1/5 and a remainder of 0. That means that and so we get 2x squared plus x minus 1 equals 1/5 x plus 1/5 times 10x minus 5 plus 0. And that means that our GCD of 2x squared plus x minus 1 and 10x minus 5 is the same as the GCD of 10x minus 5 and 0. That is clearly going to be 10x minus 5, except that it is not a monic polynomial. So what we're going to have to do is divide that polynomial by 10, or multiply that polynomial by 1/10 to get x minus 1/2, and that gives us the GCD of our original two polynomials. All right, so now I think you're ready to work on the last set of in-class activities that is called Polynomial GCD Euclidean Algorithm on the PDF file included with this video.